Hello, everyone. So today we're going to be talking about chemical storage. And we're going to start off by talking about a rather famous early case of chemical storage gone wrong. So this particular event happened in New Jersey in 1937, as most commonly known as the Fox Vault Fire. So Fox Film Corporation, now 20th Century Fox, now Disney, was one of the early film companies. And so they did a lot of production in the silent film era, which also meant that they had a lot of old nitrate film sitting around, which essentially recorded most of the early films of the turn of the century. Now, one of the reasons why this was slightly problematic is nitrate film is made out of nitrocellulose, which is essentially very flammable cotton. And even worse than that, it turns out that it can degas nitrogen oxides, so you might know these as NOx agents, under exposure to heat. Now, this is a particularly problematic case that they were aware of, that nitrocellulose can catch fire quite easily. So they went ahead and built a film storage facility, which was divided into 42 individual vaults out of reinforced concrete separated by steel doors. Unfortunately, what they forgot to do when trying to properly handle flammable materials was account for the fact that you needed to A, have good ventilation, and B, you needed to make sure that the area was properly cooled, and C, that you needed to have proper fire suppression, like fire extinguishers. Now, all of this kicked into a real bad case in the middle of July, when there was a series of 100-degree days, which essentially was causing the nitrocellulose to degas NOx agents, which are kind of unfortunate because it turns out that they are good oxidizing agents. So I have a flammable material and plenty of oxidizing agents and a lot of heat. Yep, it turns out they discovered nitrocellulose's autoignition temperature. The film canisters started to spontaneously combust, one chamber setting off another as the heat transmitted through the building. And this built up enough pressure from the NOx gas as well as from the flames that it turned out that this facility was able to shoot out flames over 100 feet out of the windows and the existing ventilation pipes. So in other words, it started to set the surrounding area ablaze, which ended up causing severe burns for several bystanders, including killing a 13-year-old boy. So, one of the big things that we can take home as a good lesson from the Fox Film Fire is that even if you have flammable materials stored in a building or container that can withstand fire or explosions, some of the important things to keep in mind is that if you have good ventilation and, more importantly, good temperature controls, you can often prevent a fire from occurring in the first place, which can be far more important. And then third of all, if you've got good fire suppression already available on site, this can help prevent a fire from spreading before it goes truly catastrophic. And it turns out that all three of these things were seriously missing in the case of the Fox Vault. So let's go ahead and talk a little bit more in detail about more lab-based chemical storage. And so a lot of these should hopefully make sense, as we've brought several of these up in our previous examples at the beginning of class. The first thing that's important to keep in mind with proper chemical storage is, again, just various safety in terms of the storage and materials, including make sure that the room and the shelves are secure. As we saw previously in the Ohio example, improper shelving caused bottles of hexanes to fall in the lab and cause the whole place to catch flame. If your bottles and shelves aren't secure, your chemicals aren't secure, and quite a number of accidents can happen as a result. Another important thing is adequate secondary storage. So make sure that you aren't trying to fit more chemicals than an area conveniently can hold. And part of this is going to be this secondary containment. You're going to want to make sure that there's always a space for chemicals in case they do break to just splash into secondary containment and not cause a rain of flammable materials all over the area. And as we already saw, ventilation can be very important. As a good rule of thumb, all of the air in the room should change over about 6 times per hour. This should prevent the buildup of any potentially toxic gases. And again, as we saw, make sure that there's appropriate fire protection to prevent chemicals from igniting each other and appropriate fire suppression. And again, we talked about this much more extensively earlier. Make sure that you segregate your materials by hazard class. Make sure to keep your oxidizing agents away from your organics and your reducing agents. And again, acids separate from bases. The number of times I've seen an acid cabinet that also contains bases is a little disturbing and very problematic, as this is just a recipe for disaster. And again, make sure that there's proper signage. Proper labeling can help avoid a number of catastrophic accidents, as well as make sure that there's appropriate emergency contact information. There should be a person responsible for safety in every lab. And this can be incredibly important, as there's probably somebody who knows what specific problems may be encountered in, say, trying to fight fire in a specific lab or room. And there's also some very important limits on flammable and combustible materials. So as we've seen previously, one of the big sources of some of these runaway fires is there's just too much flammable material all in proximity to each other. So as a guideline, try and keep the amount of flammable material outside of a flammable cabinet to about 10 gallons, and no more than 60 gallons total of flammable materials inside a laboratory, which means that you're probably going to need to limit the amount of organic solvents present, which can be problematic for some labs, as they may need to divide up their materials over several labs to prevent an unsafe buildup of flammable materials all in one place. Now, we brought up this idea of flammable cabinets, and these are essentially making sure that you have appropriate cabinets and containers that are specially designed to meet the hazards of whatever material you're working with. So it's worth noting that there are specialized cabinets for specialized conditions. And some of these may require additional venting and grounding. So for example, one of the things that you should make note of is that there is a difference in between, say, a flammable cabinet and a corrosive cabinet. Flammable cabinets are often made out of metal. They're designed to essentially contain flames and prevent and withstand explosions. This also includes things as self-closing and locking doors to prevent the material from blowing the doors open, as opposed to acid cabinets, which are generally not going to want to make out of metal, because it turns out that, well, acid dissolves metal, so that's not a good place to start. And again, sometimes based on with things such as flammable cabinets, you may want to make sure that they're electrically grounded to prevent electrical discharge from causing a unintended ignition source. One of the other important things that's worth noting is that most cabinets should also contain separate secondary storage. This way, in case one bottle breaks, it's not going to essentially cause the whole cabinet to go. As again, we saw in the case of the Ohio State, where one hexane bottle uh, broke, and it caused essentially kind of a cascade effect. And similarly, especially when working with flammable materials, sometimes you need to make use of what's called an explosion-proof refrigerator. So let's say I'm working with a lot of organic solvents. Well, a lot of these organic solvents will degas explosive combustible material. And one of the quickest ways to prevent a buildup of combustible material is to keep it cold. That said, you also want the extra security of a door that will be more tightly latched shut and will essentially help prevent something from catastrophic results if something inside does indeed explode. And we also saw something similar to this when we were talking about the organo peroxide incident in the Arkema chemical plant in Texas, where they again needed to keep the materials cold because if you reach certain critical temperatures, you're more likely to hit flash points, auto ignitions, and increased vapor pressures. So we're trying to keep all of these as low as possible to prevent any unfortunate side effects. However, there's also some other chemicals that we need to essentially account for. One set of materials is cryogenic liquids. So these are ultra cold liquids. Think about liquid nitrogen or even things like liquid helium. So one of the biggest things to keep in mind about cryogenic liquids is that what I've done is I've usually condensed gases, which means that these will naturally try and degas out. So make sure that you store these in a well-ventilated area, because it turns out if I have, say, enough liquid nitrogen vaporizing, this will start displacing oxygen from the atmosphere. So if you don't keep well ventilation, you may unintentionally asphyxiate yourself. Very similarly related, make sure that there is a pressure release valve. So if you can imagine having a liquid nitrogen container that starts going more towards gas than liquid, you're going to have an unsafe buildup of pressure, which could potentially turn your cryogenic liquid storage into a bomb. Speaking of compressed gases turning into bombs, make sure you watch out when storing gas cylinders. So again, gas cylinders tend to be very heavy, and we definitely don't want them to unintentionally start spouting off gas everywhere. So make sure that they're secured at all times by chains or straps to a wall. And make sure that if you have it secured to anything besides a wall, such as a table or desk, that you've made sure that it fits all appropriate gas storage regulations. Also, make sure that the contents of gas cylinders are very clearly labeled, because if the label goes, it's going to be very hard to figure out what the heck is in there. And it is okay to transport a gas cylinder on essentially a dolly, but unfortunately, there is a tendency of people to try and store these cylinders on dollies. That is not appropriate. It is going to be far too easy for that gas cylinder to, say, tip over, the securing valve at the top to break, and then you now have a rocket running around the lab. I'd prefer that to not happen. Also, make sure that you use the correct regulator and cap on the cylinder when you're not in use. This will essentially prevent any sort of gas leakage and release of pressure. And please try and keep all of your incompatible gases away from each other. I do not want to see an O2 cylinder next to, say, a hydrogen cylinder. This is kind of a recipe for disaster. So remember, just like with bottled chemicals, keep your oxidants and your reducing agents as far away from each other as possible. Otherwise, you got a heck of a fire hazard. And again, make sure that all cylinders are labeled empty when the gas is depleted, because otherwise it can be very hard telling whether or not the cylinder is out or waiting to be used. So one of the other things you should note is it can't really differentiate an empty from full cylinder by inspection. So in general, the only way to really test is going to be to attach a regulator, which will give you the pressure of the cylinder at any given time. You can occasionally use the weight of the cylinder as long as you know what the empty weight of the cylinder is, and essentially a ping test, which is flicking the cylinder to use the sound waves produced from telling an empty versus a full cylinder. Though you often want to be trained in to get a good sense of the quality before you try and use this test yourself. One of the other things you should note is you can't tell the contents of a cylinder just by the color. So there should always be some sort of label present at the top of the cylinder, which will tell you the general warnings and composition of the cylinder. For example, we have oxygen, which turns out to be an oxidizing gas. Go figure, there's a reason why we call it oxidizing. If you have something like hydrogen, it's most likely to be labeled as a flammable gas, but we also have relatively safe gases, but still can be dangerous, like nitrogen, which can displace oxygen from the atmosphere if used in excess. And again, toxic gases. If you want more information about gas cylinder safety, please go ahead and see these links. However, one of the other things that you should watch out for is that it is not uncommon for labs to make use of controlled substances in analysis. For example, there are several drug testing labs which need to have a set of reference samples on hand, such things as cocaine or amphetamines. And it is worth noting that these tend to require very special permits, and as a result, should be kept under a lock and key and secured at all times. And if you're using one of these controlled substances, you should always log the amounts being used and specifically why it's being used at each time to prevent essentially misuse of any of these chemicals. But again, regulation and chemical logs aren't just for controlled substances. It's also important to note that you might need to use a general chemical inventory. So you should always try and keep a centralized chemical inventory that lets you know exactly what chemicals the lab are using, how much are present, and where they are. And these have really become a very crucial aid in chemical storage, especially if you know what chemicals you possess, you're less likely to order something you already have, and have become increasingly required by federal and state governments to prevent essentially unintended waste and the presence of materials that have been phased into higher regulation categories. And again, if you want more information about chemical storage, please go ahead and see these websites. They can be very helpful. However, one of the things you should watch out for is once you've purchased the chemical and stored it, at some point, you're going to need to dispose of it. We'll talk more about that next time.